What I would like to do today is to continue the discussion we did last time. You remember about the covalent bond. Covalent bond is one possible, say, kind of bond, chemical bond, but it's a very, say, one of the most common ones. And it's also a very simple example of where you see really quantum mechanics in action in determining a lowering of the energy when two atoms get together. Okay, we have seen all the mathematics of this. We've done the derivations. We've gone through some approximations, necessary approximations in order to be able to get to the end. But at the end, we found that the energy was lowered if we were considering the linear combination of the two orbitals on the two different atoms. We saw that the formation of two energy states, one with lower energy than the other one, and the lower energy state was the one in which the wave function was a linear combination with a plus between the two orbitals, the atomic orbitals of the two original states. So what I would like to do now is start talking about extended system. So what we're going to do today is to study a system in which we have no longer just two atoms, but we have an infinite chain of atoms. This is probably the simplest example of a crystal, of a solid. So the kind of system we're going to discuss is a system which, instead of having just two atoms, right, we had two nuclei and two electrons last time, you remember. Now we're going to consider an infinite chain of atoms. So we're going to have a nuclei spaced at the distance a from one another, each one bringing an electron or more than one, depending on the atom we are considering, a given number of electrons to our system. And the goal is to determine now the solution, the wave function of, please. The goal is to determine the wave function, the energy, the properties of the electronic states in this infinite system. So in order to do that, we will use exactly the same approximations that we used last time for the covalent bond, for the two-atom system. So instead of considering just two atoms, we're now going to consider an infinite series of atoms placed regularly ordered at the same distance a from one another. I hope you understand that this is really the simplest example of a crystal. Morning. This is really the simplest example of a crystal. We have a one-dimensional system. It's not three-dimensional, it's just one-dimensional. But all the atoms are arranged in an ordered fashion. Okay, so there is translational symmetry. And it's admittedly, the simplest example of a crystal that we can think of. But it's a good starting point for us to warm up and trying to understand the properties of infinite systems, periodically ordered infinite systems, which is our ultimate goal in our study of solid-state systems. Okay, so let me use this as an example that we can actually solve exactly to try and see what are the consequences of having an infinite number of atoms arranged in a periodical fashion. So once again, we have for each atoms, we will have our Coulomb potential. We have some states here. We will denote as phi atomic. Okay, so each one of these atoms, now I need to. Okay, so each one of these atoms will have the same starting point, the same atomic state as a starting point, so there will be one here. There will be one here, and so on and so forth, right? And also on the other side, of course. So these are our original states that we assume, sorry, it's a bit tilted. It's meant to be the same energy, of course. All of them having the same energy, the same initial energy. What do I mean by that? I mean that if I look at this system as if all the other ones didn't exist, I know the solution of the problem. It's the atomic wave function, and it's the corresponding atomic energy for that state. And what I want to do now is I want to construct the wave function of the whole system, starting from the wave functions, the atomic wave functions of the individual atoms. Okay? So we're going to use exactly the same approximation, the same approach that we used for the covalent bond. In particular, we're going to write. Allow me, to change slightly the notation. Here let me use a 0. Sorry, I'm changing the notation slightly. By 0, I mean the original atomic state. Okay? So if I label the atoms as I, this one, I plus 1, I plus 2, this is I minus 1, I minus 2, I minus 3, and so on and so forth. I'm just labeling the sites. I can say that this is the atomic solution at site I. In particular, what I can say is that well, let me use just one-dimensional notation. This is what I mean by wave function phi I being the eigenfunction of the atomic problem at position Ri, right? So this is position Ri in space. I'm using the same notation I've used before, right? So Ri is just A times I. You remember, we use the same notation to denote the positions points along a one-dimensional line. So the position of point I is A times I, if this is point I, a particular point in my chain, denoted by this integer I, and its position is given by just by A times I. V is the Coulomb potential centered at Ri, right, this one. Okay, so let me highlight it. So in this particular case, this will be V R minus Ri. And the solution of the atomic problem for this particular Coulomb potential is the atomic wave function centered at I with eigenvalue E naught. And obviously what I mean by this is obviously the atomic wave function centered at Ri, obviously, right? This is the atomic function centered at Ri plus 1. This is the atomic wave function centered at different sites. So they are all identical functions. They only differ because they are centered at different places, obviously. And same with the Coulomb potential. This is all the same potential. It just differs because we are centering this potential at different sites. I'm just repeating exactly the same. I hope you recognize that we're just repeating the same procedures, the same terminology that we've been using in the past for the covalent bond and for the definition of the one-dimensional lattice. And let me now state what my goal is now. My goal is to find the solution of this Hamiltonian now. H equals to minus h squared over 2m delta squared plus sum over all i's of V R minus Ri. Right? That is, each electron in my system will be subject to this Hamiltonian containing kinetic energy and the sum of all the attractive potential due to all the atoms to the nuclei that are present in my system. Okay? Remember, last time we only had 2. You might recall that here we had only V1 plus V2 last time because we only had 2 nuclei. Now we have an infinite series of nuclei. And each electron sees this infinite series of attractive wells along this one-dimensional line. Once again, in doing so, I'm essentially forgetting about electron-electron interactions. Okay? I'm just assuming that each electron sees only the nuclei. The electron is not seeing all the other electrons. But, I mean, it's a good starting approximation at least. All right? So this is the Hamiltonian we want to solve. And this is the Hamiltonian that we know has been already solved by someone else, who is giving us the results of the atomic physics problem. But we want to solve this one, which is, of course, more complicated than this one, because here we only have 1 Coulomb potential. Here we have a sum over an infinite number of Coulomb potentials. So the way we're going to try and solve the problem is by constructing a guess for the solution. You remember last time we constructed the guess as a linear combination of phi 1 and phi 2, the 2 orbitals. And now we're just going to build this as a linear combination over an infinite set of wave functions, all the possible solutions at the different sites. Right? We're essentially trying and build a total wave function as a linear combination of this plus this plus this plus this plus this, with coefficients to be determined. Last time we had only 2, A1 and A2. Now we have an infinite number of coefficients to determine. AI. So the problem we want to solve is, of course, so the unknowns are the infinite set of AIs and the energy, the corresponding energy. Okay, let's try and apply now this wave function. This, minus. Now, let me write this a bit more. So we have an infinite sum. There will be term, at some point, term Vi minus 1. Allow me to compact a little bit the notation. So I'm going to call this one, I'm going to call it Vi. What I mean is the Coulomb potential centered at site I. Okay, so let me somehow construct this sum, and let me assume that at some point I'll get through I. I will be a generic integer. Oh, notice it's not the same as this one, sorry. Yeah, I should be more careful here. This is not a running index. It's an index I choose to fix. Let me call it J. Sorry. I need to be careful here with indices. So I is a running index. It runs over all the sites, infinite sites, from minus infinity to plus infinity. I'm taking a specific J. Okay, I'm just selecting out of this infinite sum the given J. I'm just expressing this as the sum of Vj, Vj minus 1, Vj plus 1. Of course, there will be an infinite series on the left and on the side here, on the right of that. And let me do something similar here, because I have to apply h to my wave function. So here we'll have an infinite series, and then at some point I will have j minus 1, phi naught j minus 1 plus aj phi j plus aj plus 1 phi naught j plus 1 plus an infinite series to infinity on the other side. So this is the left-hand side of this equation. I'll now come back to the right-hand side in a moment. Let me first focus on the first-hand side. And let me consider now the projection of H. You might remember the trick that we applied last time, right? We had two terms here. And we said, well, when we apply H to the first term, we're going to subdivide our Hamiltonian in a different way, right? If we identified 1, here we're going to select kinetic energy plus V1, and then separately V2. Let's do the same trick here. So let me focus now on this term, the jth term. And suppose that I want to apply H to this term now. Okay? I'm going to group the Hamiltonian in a very specific way. I'm going to do it by taking this term together, and consider all the rest as a separate object. Of course, it is obvious why I'm doing that, right? Because this plus this is exactly the atomic Hamiltonian at site J. And when I apply to this one, I'm going to get the atomic energy, right? So there is a good reason why I'm doing that. So let me rewrite this as in this form. Plus Vj plus delta Vj. What do I mean by delta Vj? I mean the full potential minus Vj, right? So by definition, this is the full potential, this one, so sum over I of Vi, minus the specifically term Vj that I extracted out. And I call it delta Vj. Just give it a name, define it. Okay? The full potential, the total potential, minus that particular term. Remember, I'm doing this only when I apply my wave functions to this one, right? So I just isolate this term here, because that's the one I'm interested in. Yes?
Why do we have to include that delta Vj?
I have to rewrite this object, right? H. This is an equality. So I'm rewriting this, and I rewrite it by grouping these two terms. Here you go. And leaving behind all the rest. Okay? And all the rest, it's this sum, infinite sum, up to Vj minus 1, then plus Vj plus 1 up to infinity. Okay? I call it delta Vj. That is the sum over all Vi's minus only one, the one that I picked, that I extracted out. Okay? It's an equality, so it has to be there, right? Otherwise, it's not an equality. Yes. Oh, they're there. I'm not listing them any longer. They will be here, of course. Here will be j plus 1. Here there will be j minus 1. Okay? By dots, all these dots, I mean all the terms that, say, from j plus 1 onward and from j minus 1 backward. Okay? I'm not writing them any longer because I'm already assuming that I'm doing this exercise. I decompose my Hamiltonian in this way only when I apply to this j term. If I applied it to j minus 1, I would decompose this in a different way. I would extract out j minus 1 and write, of course, delta Vj minus 1. Okay? So I'm highlighting this term because I'm only doing using this decomposition when I apply to this particular term. If I apply to another term, I will have another decomposition. All right? Let me write it above because, so let me define how a few things. So delta Vj is sum over I Vi minus Vj. But I don't have to, so I can use the space here below. So when I apply, there will be terms that come from the projection of whatever is h on the previous terms that I'm not interested, at least for the moment. And then I will have h, this one, times here. So the first term is obviously going to give me aj E naught phi j naught, right? By definition, because this is the atomic Hamiltonian at site j. So when I apply to the atomic wave function at site j, this gives me the eigenvalue, the atomic eigenvalue. And then I have delta Vj. Okay? Good. This is the left-hand side. The right-hand side is quite trivial, because the right-hand side is only a number times phi j. So it's E times which I can therefore write as right? Notice there's an equality here. Notice again, it's not that different with respect to what we did last time. Last time we had only 1 and 2 instead of an infinite series. We extracted out A1, E0, phi 1, if you remember. And delta Vj for us was just V2, because our total potential was just V1 plus V2. So delta V1 was V2. Okay, so this was V2. And also on the other side, there was A1, E phi 1. So I hope you just notice that this is exactly what we've done last time, simply extended to an infinite series. And with a replacement, instead of having just V2, that is the other V, with respect to the one we are projecting onto, here we have the sum over all the other ones, the infinite number of V's, which is not the J that we have selected for the projection. All right, so we are exactly the same point as we were last time. We have an equation between functions. This is a function. It's a function because these phi's are functions. Notice that E0 is not a function, but delta Vj is a function, like V2. V2 was a function. Here we have functions on the right-hand side. So we have an equation between functions, which in principle we should equate at every point. We don't do it that way. By the way, again, our goal is to determine all the AJs, the infinite AJs in this problem, and also E. So we have an infinite number of unknowns now. But again, we have an equality between functions. So if we have an infinite number of unknowns and an equality between functions, an equality between functions needs that the function needs to be equal in all the points. So it's an infinite number of equations in principle. Okay? So in order to reduce it to a system that we can handle mathematically, what we do is we take this equation between two functions and we project it onto the atomic orbitals, which is like we did last time. Last time we projected this equation, which was an equation between only 1 and 2. We projected it on phi 1 and on phi 2. Now we are going to project this equation onto a generic phi. Okay? So we take the left-hand side and the right-hand side, and we just project it onto an arbitrary atomic wave function. So let me add here Brian Katz, just to allow me to do the projection easily. So I'm going to project this equation, left and right side. I'm going to project it onto an arbitrary atomic wave function, J, K, H, let me call it L. Oh, I'm using, sorry, capital letters for atoms, so I'm using L. Okay? I'm taking an arbitrary L. L can be any number from minus infinity to plus infinity, an integer. It's taking an arbitrary one, and I'm projecting left-hand side and right-hand side on phi L. Last time we did phi 1 and phi 2. Now we do a generic L. Okay. I hope I can now delete at least this part. I'd like to keep this picture here, so I'm going to work on this side of the blackboard for the moment. Okay. Yes. Before I do that, however, I need to expand a little bit this. I need to add also the terms j minus 1 and j plus 1, because they will be relevant for my purposes. So let me, before I do the projection, let me add at least the terms, the two next terms, on the right side and on the left side. So the term on the left side will be simply a j minus 1 E naught phi j minus 1 plus minus 1 minus 1. Plus, there will be the term with j. Phi j naught plus there will be a term a j plus 1 E naught phi j plus 1 plus E j plus 1 delta v j plus 1 phi j plus 1 plus all the other terms. Okay, what I've done is I've just added two more terms, the neighbors term on the left and on the right. Okay, the reason I'm doing that is you'll see it will become clear in a moment. So let me start applying phi L, a generic phi L. To this function here. Let me do this first for let me do this first for the no, actually, let me do everything correctly. Come on. So I'll start doing the projection now. So this will be a j minus 1 E naught yes?
Do we have E0 almost a g minus 1 item?
Which one?
Yeah, those terms.
We do, because when I extract out this one, this, I'm doing exactly the same trick I used to extract this one. So I've decomposed the Hamiltonian into an Hamiltonian center in j minus 1 plus delta v j minus 1, which is what remains. Okay? Not obvious?
We did like h of j plus delta of vj, right?
Right, delta vj.
Yeah, and then we have on the case.
Yes.
And then we'll have h of j onto j minus 1, h of j onto
No, 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 no. No, no. When I apply, remember, when I apply to a different j, which is not j, I rearrange the Hamiltonian. So I write it as h atomic of j minus 1 plus delta v j minus 1. So every j, I change the way I rearrange the Hamiltonian. Okay, so this is the result of applying the atomic Hamiltonian on j minus 1 and leaving behind delta v j minus 1, in fact, because I removed the j minus 1 term out of the Hamiltonian. And same for j plus 1, of course. In order to write this, I just rearranged the Hamiltonian in such a way that I could extract the atomic term here, and I'm leaving delta vj plus 1, because I've removed the j plus 1 term from the Hamiltonian. Okay. Good. Now, let me proceed with this one. So here I have phi L0 phi j minus 1. No, wait. Before I do that, I need to, make another statement. Now, this function here, it is an infinite function with an infinite number of terms. Okay? And I've just selected out this j, the j minus 1, the j plus 1, and then I'm writing the rest of dots as dots. But it's, in principle, it's an infinite series from minus infinity to plus infinity. Good. I'm going to project it on L now, an arbitrary L. Now, because L is arbitrary, I can arbitrarily choose out of my infinite sum j to be L, right? I don't need to take an arbitrary j. When I write this infinite equation, I can say, well, instead of selecting j, let me call j L. There's no reason why this needs to be different from L. This is an infinite sum, so I can pick up any point in the infinite sum. In particular, I can pick up exactly L, right? So I can say, well, this is not an arbitrary j. I mean precisely this L when I do L here. If I change the L, I will change my center here in my sum. Okay? I'm allowed to do that because in principle I've done it for an arbitrary j, and I can always say that this j is exactly the one that I'm going to project my wave function on.
Is this function orthogonal?
I'm coming to this orthogonality in a moment. For the time being, they're all atomic wave functions. Okay? So this j actually can be L. I can say, okay, that j is L. In fact, the way I do it is actually, instead of changing all the L's here, allow me to change the L here, okay, and call it j. I'm just picking one arbitrary j, and I've selected out of the infinite sum to the center, I choose it to center it in j. Okay? It's just an index, right? So I can call it j, L, whatever I want. The point is that when I project my wave function from the outside, I can choose to highlight precisely the term that corresponds to my atomic wave functions that I'm using to project thing, and just leave all the rest as dots. It's my choice to put my spotlight on a particular term. Okay? So instead of calling L, let me call it J, because this at least will allow me not to change all the J's into L's here. It's just a notation, it's just an index, so I can call it J if I wish. So the way the argument goes now is actually is slightly different. So it's say, okay, let me pick an arbitrary atomic wave function j. Out of the infinite sum here, I'm going to pick up precisely the term j. Just put the spotlight again. Okay, j is there. And then all the rest will be dots. And let me proceed with the projection now. This dot, 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 plus aj E naught, phi j naught, phi j minus 1 naught. Hey, but this is something we discussed already the other time, right? Wave function centered at j, wave function centered at j minus 1, we assumed that the overlap is 0. Again, they are not orthogonal. There's no reason why they should be orthogonal. These are two solutions of two different Hamiltonians, one centered in j, the other one centered in j minus 1, atomic Hamiltonians. No reason why they should be orthogonal. We assume that the overlap between a wave function here and a wave function here is small enough that we can neglect it. All right? So here we put the usual statement that in red, the approximation. So any I, j is different than 0 only if I is equal to j. But of course, if I is equal to j, it's the same wave function, and so it's 1. Okay? So this is not, actually, let me put approximately so that we remember that this is not an exact statement, and it doesn't come from some orthogonality due to the fact that these are two eigenvalues, eigenfunctions of the same Hamiltonian. Nothing like that. It just comes from the fact that they are distant and they are exponentially decaying. And so we approximate the overlap to 0 if they don't belong to the same site. If they belong to the same site, then of course it's 1 because it's the same function. So this one we already know. It's going to disappear from our expression. Let me continue. Delta Vj minus 1, phi j minus 1. That's the, phi j. I'm projecting on j. So these are the first two terms. Third term, what's going to happen if I project it on phi j? 1, right? So this is just aj E naught. Fourth term, well, here I have to write it explicitly. aj phi j delta Vj phi j naught. Plus, the first four terms are done. Let me continue with the last two terms. aj plus 1 E naught phi j plus 1. 0. So this also disappears. We have the last term. aj plus 1 phi j delta v j plus 1 phi j plus 1. Oof. You're right. aj minus 1. Thank you. aj plus 1, aj plus 1. Correct. Oof. Okay. Do you allow me to erase this one? I still have to do the right-hand side. Huh? This is just the left-hand side. I still have to do the right-hand side. But let me simplify a little bit the left-hand side first. Okay, so this term here. Let me consider this object. What is this? This is wave function at j. Wave function at j minus 1. So if I'm here, suppose that this is j. Wave function here times wave function here times the total potential minus the potential at j minus 1. What do I mean by that? Let me draw it, because what I mean by that, green color. I have to sum all the potentials, this one, plus this one. And then when I get to this point, I have to remove the j minus 1 potential. Okay, so this will become long thing here. And then it just continues like this. Okay? So this is delta V j minus 1. It's the sum of all the Coulomb potentials minus this one. I've removed this one. So, once again, wave function at j, or I, times wave function here at j or I, times this green line. Okay. You might remember that this is in last time, when we only had two sides. If this was 1, delta V1 is actually 2, because it's the total potential minus 1, so it's V2. So this is phi 1, V2, phi 2. We gave it a name to this, right? We called it T, hopping. Let me call it T for the time being. Let me use the same name. Let's see, this term here now, the last one. What is it? Phi j, phi j at a given site. Phi at another site. Delta V j plus 1. So it's the green potential, but now centered here, j plus 1. Okay? Wave function at the nearby site. Wave function at this site, which is the site where I have the missing potential in my potential. Isn't it the same as the one I discussed before? Before I had wave function here, and the potential which was missing the term here. The only difference is the mirror symmetry. I'm just reverting everything. But I mean, when I carry out the integral, mirror symmetry is there. So I don't, the result is exactly the same number. Okay? I hope you see it, okay? Wave function, potential missing a term here. Here I had wave function, potential missing a term here. The only difference is that I just moved this by, well, everything has been moved by one side, and I've reverted the order of the two, so that the potential missing a term is now the one on the right-hand side instead of the left-hand side. But by mirror symmetry, the result of the integral is the same. So if I call this t, this is also t. Same number. What about this term here now? Wave function at a given site, wave function at a given site. In our language of last time, if this was 1, was phi 1, and V2. Right? Because delta V1 is V2. So we call this delta E0, the on-site term. Okay, so we have simplified our notation considerably. Well, what about the other terms, the one that I'm now describing as dots? Well, the other terms, okay, if I go further to the left here, there will be terms with phi j times phi j minus 2. There will be terms of this sort, and terms of this sort are 0 because of my rule, and terms of this sort, where here I have j, and here I have j minus 2 and j minus 2. Well, if I've neglected the overlap between wave functions here and here, there is even more reasons to assume that if the two wave functions are two sides further away from one another, these terms are going to be even smaller. So remember, last time we were not even sure whether we would keep this term in light of the fact that we neglected just the overlap between two nearby sides. Okay, we said, well, let's keep it. I'm not going to explain why we keep at least this term. But certainly, if we decided to neglect nearest neighbor terms here, and we decide to keep at least this one, certainly if I go to j minus 2, the overlap is going to be negligible. Okay, so I don't need to write anything here. This is just going to be 0. Or at least small enough that I can neglect it. Same argument for the points here, for the dots here. All the points, the additional terms here in this expression will be expressions of the time phi j plus 2, phi j plus 3, phi j plus 4, and so on and so forth. So I'm going to consider overlaps of my wave function j with wave functions sitting at 2 or 3 or 4 or 5 sides further away. In the spirit of my approximation that the wave functions decay exponentially, I'm certainly going to be able to neglect all these terms. Okay? So at the end of the day, I'm not left with too much. I'm left with 1, 2, 3, 4 terms, which I can write in a very compact way now that I have introduced my notation. Okay, so this is just a j minus 1 t plus a j e naught. Actually, I can group this plus delta e naught plus the fourth term, a j plus 1 t. And that's it. There's nothing else. Because there's nothing else to the left, nothing else to the right. Just 4 terms, actually 3, if I compact the central one. Okay, now it's time to look at the right-hand side. Let me just remind you what the right side was. It was E times the series of the wave function, right? So the sum over all the A, I, phi I. And remember, I have to project also the right-hand side of the function onto phi j. But if I project phi j onto the sum of all my phi's, well, it's simple, because I can just use the orthogonality. I can just use this statement here to just select phi j. So obviously, the right-hand side will be E aj, period. Phi j, which is 1. Right? So when I project just psi, right, I have to project E psi onto phi j. E is a number, so I have to project psi onto phi j, but if I project psi onto phi j, I'm just going to pick phi j out of here. And this will be proportional to aj, obviously. Now, once again, let's look at the analogy between this and what we've seen last time, the covalent bond. You might remember that last time, if j was 1, okay, we had A1, the on-site term, plus A2, t. Of course, we didn't have E0 because there was nothing on the left side, right, for the two atoms. And here we had E1. So the main difference here is that we are adding one term on the left-hand side. So every atom has not only a neighbor to the right, but there's a neighbor also to the left. So two neighbors. So there are two hopping terms here, on the left and on the right. Last time we only had one, either on the right if it was 1 or on the left if it was 2. The other big difference is that this is not an equation for two unknowns, but it's an equation between an infinite number of unknowns. Because I have to determine all the AJs, not just one, not just two. This has to be true for all AJs. So it's no longer an equation between two unknowns, actually two equations for two unknowns. It's an infinite set of equations, because for Hj there is a different equation, for an infinite number of unknowns, all the AJs. Okay? And these equations are all coupled to one another, because J1 is coupled to J, right? This equation contains J, but is coupled to Aj minus 1, and it's coupled to Aj plus 1. So they're all coupled to one another. I cannot decouple them into blocks. They're all coupled, because J is coupled to J plus 1. If I write the next one for J plus 1, it will be coupled to J plus 2. J plus 2 is coupled to J plus 3, and so on and so forth. Okay? So there's no way I can trivially decouple these equations into blocks. In fact, let me write this as an equation between vectors. So you remember last time when we had A1 and A2, I rewrote the two equations as an equation between matrix times a vector equals to eigenvalue times vector. And the vector was A1, A2. Now the vector is not A1 and A2 only, but it's a vector of infinite length. Okay? A minus infinity to A plus infinity. There will be infinitely many terms in my vector. So let me write now this equation into an infinity by infinity matrix equation. Here I will have infinite many terms. I pick the Aj1 here. And of course there will be the next one. The one before will be J minus 1. The one afterward will be J plus 1. So it's an infinite vector containing an infinite number of elements. Let me first write it, and then we'll discuss it, okay? So this is row J in my infinite matrix. And this is actually column J. Okay, so this term is the diagonal term, this one here. We're taking a point along the diagonal, J, J. I will now construct the other ones in a moment. So let me take the product of this row here with the vector, right? If this is a term J, clearly I will have zeros all the way up to this point, then T times Aj minus 1 plus E0 plus delta E0 times Aj plus T times Aj plus 1, and then zeros. This is exactly what I have on the left-hand side, right? Right-hand side, the J terms is Eaj on the J row, right? This is the J row. So this equation here is just the equation between of the J term of the vector. That is the product of this times this equal the E times AJ term. Now, what if I move one step up, for example? I go to rho j minus 1. Well, once again, there was no reason why j was j. This is true for any j, right? So if I go to the previous one, it will continue to be true that the central term will be the one with E0 delta E0. Because this equation, I can write exactly the same equation for j minus 1 if I wish. J minus 1, here there will be j minus 2, here there will be j, and here there will be j minus 1. I can just change name to j. This is true for any j. The important thing to remember is that this j has to be the same as this one. And this has to be plus 1, the central one, and this has to be minus 1, the central one. So if I construct my matrix here, I will have that if I go one step above, well, it will just continue to be on the diagonal. And all the rest will be 0. Right? So this will be now the j minus 1 term. And obviously I can continue here. Oops. E0 plus delta E0 t, and so on and so forth. In other terms, there will be along the diagonal, I will have E0 plus delta E0, and one position out of the diagonal, everywhere, I will have t above and t below. Once again, analogy with what we did for the covalent bond. We had only two sides, so we were working with a 2 by 2 matrix. I hope you recognize here the 2 by 2 matrix that we were working with last time, right? E0 plus delta E0 along the diagonal, t off the diagonal. Here we are just constructing something which is no longer 2 by 2, but it's infinity by infinity, because we have infinitely many degrees of freedom here. We have infinitely many AJs to determine, coefficients to determine. Right? So we need to determine a vector. These are all our unknowns that contains infinitely many terms. And this vector, which contains infinitely many terms, is the solution of a eigenvalue problem for this infinitely large matrix H, if you wish, made of a diagonal term and an off-diagonal term that is t, just one element out of the diagonal. So if we want to find out the AJs and our energies, what we need to do is to diagonalize this matrix, find out the eigenvalues and eigenfunctions and eigenvectors of this matrix problem. Of course, it's not simple. It's not simple because it's an infinity by infinity matrix, first of all. It's just a 2 by 2. And there's no way I can decompose it in blocks, right? A big matrix, if I can decompose it in blocks, I can diagonalize block by block. But here, you can rearrange your rows and your columns as you like. No way. There will always be a coupling of one term with another one, and so on and so forth. This is coupled to the next one is coupled to the next one, and so on and so forth. There's no way I can rewrite it in block form in such a way to diagonalize first one term and then the other term separately. I'm forced to diagonalize this object as an infinity by infinity matrix. On the other hand, there are two important properties, very nice properties that this matrix has. The first one is that this matrix is translationally invariant. Right? If I sit here, I sit here, I sit here, I'm going to see exactly the same matrix. I can translate everything by 1 or by n, of course, in the two directions, rows and columns, and my matrix will look exactly the same. Right? Notice this is infinity by infinity, right? So by shifting by 1, it's not going to change anything. So if I shift by 1 in both directions, columns and rows, this matrix will remain identical. So this is an important property which we're going to exploit in a second. Yeah?
I think we can write it probability that an electron can jump from the left?
Yes?
Okay, because we associate AJ like the square of AJ like a probability, and then we
Yep.
put some
Okay.
factor T, and then okay, so the particle to stay at J's
Yeah.
depends on the probability that an electron that comes from the left, and then from the right, because we have J minus 1 and J
Yes.
plus 1. Okay, I mean, we can argue this way, so why?
Okay, so your argument is this. I mean, we can always argue that the probability of an electron at a given site is the probability of an electron coming from the left and from the right.
Yeah.
And I don't really see how you can formalize this into a... I understand your hand-waving qualitative ideas, and more or less, I mean, this is the correct idea. But we need to formalize, right? We need to do it mathematically. So mathematically, the only way to proceed is to try and solve this mathematical problem, right? So also, you shouldn't really see it in terms of dynamics, right? Here we are looking for the ground state. We're not looking for a dynamical process. So when I say that this term T is hopping, you don't have to be misled. We're not talking about a real dynamics of the electrons here. In fact, T will enter also in the dynamics, but so far we have not considered any dynamics. Here we're looking just at the ground state. Okay? The reason we call it hopping is because eventually, in more elaborated theories, this will also determine the rate at which electrons will jump from one side to the other one. But in this particular context, there's no dynamics. We're just looking for the ground state. Time is not present in our picture. We're solving the time-independent Schrödinger equation. So there's no time, there's no flow of electrons, there's no jumps. It's just an overlap so far. Okay? I appreciate, however, your statements, and this goes in the direction of understanding how then processes like transfer of electrons take place. But so far, we are not concerned with that yet. Okay? So what I want to appreciate is, at this point, is only the mathematical, the features of this mathematical problem. We have an infinity by infinity matrix. There are a number of problems. I mean, it's infinity by infinity, and it cannot be decomposed in blocks. So we have to solve it, brute force, like an infinity by infinity matrix. There are two advantages. One is the translational property. The second one is that there are only elements extremely close to the diagonal. If this is an infinity-infinity matrix, you have to think that here there is infinitely many, say, places, objects, matrix elements, and they're all zero. This matrix is only non-zero. This is infinity by infinity, essentially infinitely close to the diagonal. All the rest is zero. Because if I sit here, it's going to be zero. I'm very far to the diagonal. So every element outside the diagonal and the first line here, one step off the diagonal, is zero. So it's a matrix that, assume if you think of it as an infinity by infinity matrix, the non-zero terms only, are restricted to essentially a line in this infinity by infinity. So there are infinitely many more zeros than non-zeros in this matrix, right? Because only along a single line, or actually three lines, you have non-zero elements. All the other elements are zero. So there are infinitely many more zeros in the diagonal than non-zero elements. Okay, so it's a very simple Hamiltonian. It's not an Hamiltonian that fills infinity by infinity where all the elements are non-zero. They are non-zero only along a very, very narrow range close to the diagonal, if you see it, of course, as an infinity by infinity matrix. How are we going to solve this matrix problem? Well, we have to use some sort of educated guesses about the solution of this problem. So what I'm going to do now is to tell you one possible class of solutions of this Hamiltonian. This is, by the way, a very recurrent Hamiltonian in solid-state physics. Okay? You'll find it several times. We'll actually find it again in the future. The same Hamiltonian, mathematical structure, the same mathematical structure. Okay? So while I asked you to remember by heart the solutions of a 2 by 2 Hamiltonian A, B, B, I don't ask you to remember by heart how to solve this one, but I ask you to pay particular attention to the mathematical problem, because this is a very recurrent problem in solid-state physics, that is when you have this translational symmetry. So let me state now one possible class of solutions of this problem. And I claim that the possible solution of this problem is saying that Aj is equal to e to the I qj. Q to be determined. Okay? That's my argument. It's my, say, assumption, my Ansatz, as we say in physics. Okay? I say, okay, I tell you this is a possible solution to this problem. Notice that by this I mean all the j's, because I can express every j in this form, right? So this is actually not just one, it's all possible j's are written in this form, where q is something to be determined. Let's see the possible values of q's, and whether, of course, this expression solves our problem, our infinity by infinity problem. Well, let's try. Let's take rho vector equals to here, which is essentially this equation. So what we have to prove is that this solution solves this problem for every j, right? In this way, we will be able to show that every line times rho times vector solves the problem. So let me try and put this expression into my expression for an arbitrary j. And I have to show that this is true for all j's, that this solves the problem for all j's. Okay, so let me do it. E to the I q j minus 1, yes?
Is this just because, or we have some reason behind it?
This is Bloch's theorem, okay? So we'll get to Bloch's theorem in a moment, actually probably next time. But here I'm doing nothing else than re-expressing Bloch's theorem in a different way.
One more question. Is
Yeah.
Q complex or real?
We'll see. We'll see. For the time being, let's assume it's real. Okay, very good observation. Is it complex or is it real? Suppose it's complex. Suppose what's happened if it's complex? If it's complex, there will be an imaginary part, and the imaginary part will be such that Aj will either explode for j going to plus infinity, or explode to j going to minus infinity, depending on the sign of the imaginary part, right? So we clearly don't like those kind of solutions. We don't like solutions that become infinitely large at minus infinity and plus infinity.
Okay, one more question.
So sorry. The conclusion of this statement is that, okay, let's choose Q to be real. Sorry, second question.
Because we write the wave function as a linear combination of those psi I with a coefficient AI.
Right?
One of the postulates of quantum mechanics is the norm of those coefficients.
Sure. Okay, another good point. Sorry. So your statement, what you're saying is that, yes, we're expressing this psi as a linear combination of AI, and we want to make psi orthonormal, or, normalized to 1.
Yeah.
Let's do it. Let's do psi, psi. Psi, psi, thanks to this one, okay, is the sum over all i's of AI squared, right? So I want this one to be 1. Big problem, right? What are we going to do now? If we want this one to be 1, and we express, by the way, Aj in this form, AI squared will be 1. So how can we make this 1 if we are summing over an infinite number of 1s? We have to do something, right? I hope you have seen this problem already in particle physics, in quantum mechanics. This is not the correct way to normalize functions that extend over an infinite range of, spatial range. So this is actually not a good choice for the normalization. We don't want wave functions to be normalized to 1 over an infinitely large space. take plane waves, right? Plane waves, how can you normalize to 1, a plane wave, right? If the volume is infinitely large. Now, I actually have to say that this problem is more serious in free space than here. Because here, we can still decide, if we wish, that our wave functions are normalized, for example, to 1 if I take this integral over, for example, a unit cell only. Okay, I could say, well, I take my wave function, and instead of asking my wave functions to have the integral of its square modulus to be 1 over the whole space, let me ask that my wave function is integrates to 1 only within the unit cell. Now I have another problem. My wave function could be different if I go from one unit cell to another one. So how can I argue that it's 1 in one unit cell? What about the other unit cell? If the wave function is different in the other unit cell, I mean, I have to do it for all the unit cells? Allow me to come back to this problem when we discuss Bloch's theorem, so next time. So I'll discuss it explicitly, this problem of normalization. For the time being, let's assume that the wave function is normalized in such a way that it is 1 per unit cell. In other words, that I can make each one of these elements 1. I just need to do that. And then, therefore, this is OK, because this is normalized to 1. In each unit cell, for each j, the square modulus is 1. But I'll come back to that if you don't.
Yeah, it's okay. But another concern, if you take this thing,
Yes?
in which regions are we? I mean, if we are near the potential, then I mean, we can. This looks as if like a plane wave and like a free particle.
Well, OK, your question is, this looks like a plane wave, right? I have to repeat it, right, because of the recording. So you say, this is like a plane wave. How can we somehow tell this wave function that there is an attraction here? There is a... Don't forget that this multiplies the wave function. So the real wave function is aj times the atomic wave function. So don't see this as the wave function. This is not the wave function. This is just the coefficient that multiplies the atomic orbital. So my wave function will know that there is a Coulomb potential, because to each coefficient, it will have the atomic wave function attached. OK. Exactly. So this is not the wave function. OK. This is a very good observation, because this is not, say, well, I mean, those of you who are familiar with, sorry, no, it will take too much time to make the analogy. I have to finish this, otherwise we'll, if you wish, we can discuss later on some more, I mean, mathematical consequences of these statements, of this, what we are doing. For the time being, let me proceed, OK? Let me proceed. So I'll come back to normalization. Let me assume that I can take AJs to be normalized to 1, but I'll come back to that next time. And let me proceed with the with verifying that this is actually correct. T plus AJ, so AJ is EQ, J, E naught plus delta E naught plus EIQ J plus 1 T. And this must be equal to E Q Q J. OK. So I'm trying to verify that this is a possible solution to my infinity by infinity matrix problem. So I'm taking one arbitrary line, J, and I'm trying to see whether this expression solves the equation for an arbitrary line of this row of this matrix equation. Okay, here I can clearly simplify this equation because I can remove e to the I qj everywhere. This disappears, this disappears, this disappears, this one disappears. Okay, I'm removing e to the I qj everywhere. And what I'm left with, actually, let me group now terms. I'm grouping the term with t first term and last term of left-hand side, e to the minus iq plus e to the iq times t, plus e naught plus delta E naught equals to E. But this object here is what? Twice the cosine of Q, right? So let me actually revert this and say that E is equal to E naught plus delta E naught plus twice T cosine of Q. So we started from a guess for the solution with an arbitrary Q to be determined. Q, we argued, must be real, because if it's imaginary, we're going to have exploding solutions. Fair enough. Let's keep Q as general as possible. We find that the solution exists for an arbitrary Q as long as the energy that corresponds to that particular Q, that is to that particular solution, is given by this expression, E naught plus delta E naught plus 2t cosine of Q. In other words, I found infinitely many solutions to my problem. For every Q real, Aj equals to EIQJ is a different solution. It's a different set of infinite numbers, right? If I change Q, it will be a different set of infinite numbers. For example, Q equals to 0. All the ij's are 1, right, for every j, correct? If Q is equal to 2 pi, what are the aj if Q is equal to pi? They are all 1 again, okay? Well, that's an exception. If Q is an arbitrary number, 0.1, well, these aj's will be some numbers, okay, a series of numbers. So every Q gives me a solution. Solution meaning an infinite set of numbers that solves my problem with eigenvalue given by this as a function of Q. Okay? So in this way, I actually did find not only 1, not 2, not 3, but infinitely many solutions to my problem. Last time, you remember, we had 2 wave functions, 2 atomic orbitals. It was a 2 by 2 problem, so we could only, of course, find 2 eigenvalues for a 2 by 2 problem, plus and minus. Here we have an infinite set of, my wave function, my eigenvector is infinitely large, but I still find infinitely many possible solutions, not just 1, not just 2, but infinitely many. And they can be labeled. I can label each one of them with this number Q. A different Q will give me a different set of a different eigenvector and a different eigenenergy expressed in this form. Okay? So I have a number of solutions which is equal to the number of real numbers. Every different real number will give me a different solution. Not exactly, because we already noticed that if Q is equal to 0 and Q is equal to 2 pi, we get exactly the same solution. Do we get the same energy? Do these 2 solutions have the same energy? Look at here. If Q is 0 and Q is 2 pi, it's the same number. Okay? So in fact, this is true, but there is a lot of redundancy when I do this. Q belongs to R, but there is plenty of Q's for which the solution is exactly the same, both in terms of eigenvector and in terms of energy. In fact, if I take an arbitrary Q and I add to that Q 2 pi, Suppose I take an arbitrary q and I add to that q a 2 pi. What's going to happen? I'm going to multiply this times I 2 pi j, but that's 1. Okay? So if the problem is solved for a given q, q plus 2 pi gives exactly the same solution and exactly the same energy, obviously, because the cosine is periodic in 2 pi. So there's something interesting here. I did find an infinitely many solutions, but yes? Why did I choose this function? Oh, you have to trust me. It solves the problem, right? So you agree with me that this... Okay, that's a very good question. Does another expression for AJ, something else, I don't know, the arctangent or something else, solve the problem? This is not, we are not going to show this. However, when we will discuss Bloch's theorem, we will notice that this is the only possible solution to the problem. Okay? So I'll have to do it later on to convince you. We'll have to wait a couple of lectures before I can convince you that this was the only possible solution. But you're right. I mean, the argument is correct. I gave you a given solution, and it solves the problem. Okay, I'm very nice. But I mean, what about other possible solutions? You can actually show, well, we're not really going to show it, but you're going to see it more explicitly when we discuss Bloch's theorem, that this was really the only possible solution. There were no other solutions to the problem.
What about the hyperbolic solution without hyperbole?
Well, it's the same as saying that Q can be imaginary, right? But if Q is imaginary, or if I take this to be a minus or plus, it's going to diverge, either on the left or on the right, or on both if you take the hyperbolic functions, right? So we don't like diverging solutions because we wouldn't even know how to normalize them. I mean, it's a mess. I mean, to have something that diverges at infinity. We need I mean, those solutions might exist if we had a boundary at some point. But this is not what we're doing. We have an infinite system, and we want to find solutions for the infinite system. It's like the plane wave problem, right? Exponential functions, exponentially decaying functions do solve the Hamiltonian for a free particle. But we don't like exponential functions, I mean real exponentially decaying functions, because if they decay exponentially on one side, they diverge exponentially on the other side. So there are a number of problems that... Okay? So this is a solution. I didn't yet tell you that this is the only possible solution. You'll see it later on that this is the only possible solution when we will discuss Bloch's theorem later on. All right, so we have infinitely many Qs. So let me now do the following. Q here. And for example, plot the possible energies as a function of Q. We have an infinite range of possible Qs, and I'm going just to plot this function. Well, this function will have an average value of E0 plus delta E0, right? A constant, plus an oscillatory function centered around this dashed line with amplitude plus and minus 2t, and period 2 pi. So let me draw here 0. Here I will have 2 pi. Here we'll have 4 pi, minus 2 pi, and so on and so forth. Okay, let me start with q equals to 0. Q equals to 0, E0 plus delta E0, obviously, plus 2t. Now, the sign of t. What is the sign of t? I need to know it, right, in order to draw my function. But if you remember, t was the overlap. Well, it's somewhere there, I mean, I removed it. But it was the overlap between a function, another function, and a potential. This is positive. This is positive. The potential is always negative, so t is always negative. At least if the wave functions are only positive. Okay, so certainly for S states. So we assume here that T is negative, as we did last time, if you remember. But it can be positive. It can be depending. We're just assuming that it's negative. So, yeah?
I have a question.
Yep.
I think I misunderstood something there.
Mm-hmm.
AJ equal to EIQJ, the solution there.
This one here, yes.
Okay, J is, it can be any number and also Q.
Yes, right.
Then if we fix J, then we have infinitely many solutions for one J.
Yeah, but that's not the right argument. So what you're saying, if I fix J, I have infinitely many solutions for... No, sorry, if I fix Q, now what do you say? If I fix
Yes,
J...
because both of them can have any number.
Yes, but you have to be careful. The solution, one solution, is defined by an infinite set of A's for every J. That's one solution, okay? A solution is a vector, right? It's a set of numbers. I need to know infinitely many numbers. That's one solution. It's a wave function. If I know the wave function, if I tell you what all these numbers are. So one particular solution is defined by an infinite set of numbers, the AJs, AIs, whatever. So what I'm doing here is I fix Q, and for a given Q, this gives me an expression for all possible J's. So a given Q gives me one solution to the problem. Another Q will give me another solution to the problem, that is, another infinite set of AJs, which typically differs with respect to the previous one, with some exceptions, of course, like 0, 2 pi, and so on and so forth. Okay? Is that clear now? Okay. So this solution is not just one number. The solution is the series of this for all J's. That's one solution. This is what defines my wave function. Okay? So now I say Q labels different solutions, different or same solutions, but it labels solutions. If I choose a different Q, I will have another solution. Okay? So Q is an index that tells me which solutions I'm considering. Remember, last time we had plus and minus to distinguish solutions. Here, instead of plus and minus, we have a continuous index that defines solution. This is a solution, this is a solution, this is a solution. All different Qs are different solutions. That is, are different infinite series of numbers with this particular eigenvalue. Okay? Good. So, we are now here. We say 2t is negative, so let's say that this is 2t. Well, it's minus 2t. It's 2 absolute value of t. Okay. At cosine equals to pi, it will have its maximum, obviously. Right? So if I have a 2 pi, it will go like this. Actually, let me use a color here. So the solution will be like this. Oops. And so on and so forth. Okay? So it will be an oscillatory function with amplitude, well, twice 2t2. So 4t. Sorry, t2, t. So the total amplitude is actually 4t. The total amplitude of that, of the solution. Another thing we've just argued is that if I take this solution, for example, for this particular Q, this particular solution, if I shift the solution by 2 pi, right, or actually an integer times 2 pi, that is, if I take a given Q and I add 2 pi, an arbitrary integer, positive or negative, I'm going to find not only the same energy, but also the same solution because if I change Q and change it into a Q plus 2 pi n, right, E 2 pi n j is 1. Is that clear to everyone? Do I need to write it? Let me write it. So if e to the I q j is the solution for a given q, let me add to q 2 pi n. So take another. So e to the I q plus 2 pi n j is equal to u eq iq j plus times, e to the I 2 pi n capital J, but n capital J is also an integer. So 2 pi times an integer gives me 1. So if I translate my solution by an arbitrary integer times 2 pi, I get exactly the same solution, not only the same energy and same solution. So I have a lot of redundancy, as I said before. It is true that all these Q's give me a solution, but many of them are actually the same solutions. Yep.
What does it mean that we have a kind of translation in Q?
Okay, that's a good point. We have translational symmetry, right, in Q, in some sense. Yes. What does it mean, you're asking?
Is there any physical property that expresses Q?
Not really, not really. I wouldn't really say that. You're asking whether this expresses some physical property. Not really. It is, I would like you to think of Q as a good way to label solutions, like the principal quantum number of the hydrogen atom or the angular momentum L. These are all indices that label solutions. The solution of the hydrogen problem can be classified with 3 numbers, right? N, L, and M. Here the solution can be classified in terms of Q. I give you Q, and you tell me the solution. Okay? So in this sense, Q should be seen as a quantum number. In quantum mechanics, whenever you have something that labels a solution, it's called a quantum number. It's something that if I give me that number, I can tell you what is the solution, which solution you're talking about. Okay? If you say that n is equal to 1, L is equal to 0, and M is equal to 0, I know you're talking about the 1s state of hydrogen, 1s state of the atomic problem. Similar here. So if you tell me Q is equal to 0.1, I know precisely what you mean. You mean the solution where here I need to place 0.1. Okay? We'll come to the ground state in a moment. We haven't discussed ground states, yes. So far, we are discussing the spectrum of the Hamiltonian. We are not discussing the ground state. But I need some time before we can discuss the ground state, okay? Actually, let me anticipate the discussion a little bit since you asked. So you're asking, what is the ground state? Well, obviously, if you have a spectrum of energies, the ground state is always the lowest available state, right? Okay? Okay, first problem is that it is translation. But that's not the real problem, because we already noticed that this is exactly the same. So I can actually remove it from the picture. It's not another state. This is not a degeneracy. Because if I take this and this, they are exactly the same state. They're not 2 states which happen to be degenerate. So I can remove all this degeneracy. I can be left with only 1 state in principle. The problem is another one. The problem is that I don't have a single electron here. How many electrons do I have to place in this energy spectrum? I have infinitely many, because I have each atom will contribute with 1, 2, or 3, or whatever number of valence electrons it has. So here I have a continuous spectrum. That is, I have infinitely many possible values of the energy. Infinitely many because this is clearly a continuous. I mean, if I go just to, even if I go from a finite length in Q, there will be an infinite number of possible solutions. And then I have infinitely many electrons to place there. So what am I going to do? How am I going to put infinitely many electrons into infinitely many states? That's something we're going to discuss next time. Okay? So the concept of ground state, you have to be careful because it's not just one state, because you have to fill the system with infinitely many electrons, not just one, unfortunately. But we'll come back to this next question. Now I wanted to discuss the first part of your question, that is, what can we do about this periodicity? Can we simplify our problem and get rid of all these spurious solutions which are identical to the one? Suppose I take Q, I know that if I move around away from Q by 2 pi n, I get exactly the same solution. So let's try to get rid of them. In other words, I know that there is a periodicity here given by 2 pi. If I move by 2 pi, I'm going to get exactly the same states. So how can I simplify my life and remove all the unnecessary solutions? Well, if it's periodic, I just to limit myself to a segment of length 2 pi. If I limit myself to a segment of length 2 pi, I automatically excluding all the redundancies, right? Because if I move away, I'm sure I will find something that is inside. So I could do this. I could say, well, let's focus ourselves on this range here. Let me say, okay, Q varies only from 0 to 2 pi. Fair enough. I don't lose anything if I say this, because whatever solution I find outside, there will be exactly the same solution inside this segment if I translate by the appropriate number of 2 pi's, 1, 2, or 3 times n times 2 pi. I don't need to go outside. I can live my life between 0 and 2 pi, and I'll be able to find all possible solutions. Because every solution that is outside, I can bring it back inside 0 to pi, and I will find exactly the same solution with an appropriate translation by 2 pi times n. Okay?
Please, will this sum always positive?
Which sum? This thing here. So you want to know if this is always n? Oh, no. Actually, sorry. I wrote it like this, but clearly E0 plus delta E0 is a negative number. Sorry. Yes, you're right. I should have placed the axis above here. Yeah. Sorry. It's just an arbitrary scale here. Yes, there is an arbitrary constant that I'm adding. You're right. Correct. Yes. Okay. Fine. So I'm in a space which is the space of Q's. It's infinitely large. And I say that I say that my solutions are periodic with periodicity 2 pi. In the language of that we've introduced in the first lectures, I can think of these points as points of a crystal, and this one as a unit cell. I can say, well, I can use the same language and say, look, I have a function which is periodic. I can say this 0, 2 pi, 2 pi are points on a crystal. It's a one-dimensional crystal with the length of 2 pi. And this is the unit cell. Right? It's just using a different language to call something we are very familiar with. In fact, what I can tell you is that the most natural choice for this segment is not between 0 and 2 pi, but it's the Wigner-Seitz cell, the one that goes from minus pi to pi. That's the most natural choice for... so we're not going to choose the one from 0 to 2 pi, we're going to choose the one from minus pi to pi as the natural choice to describe our functions. It's an equally valid choice, right? I can still choose this segment or whatever. Any segment of length 2 pi would work. So let me choose for simplicity the one that goes from minus pi to pi. So I'm going to say now that Q here actually is not just a real number. I'm going to say that Q goes from, from minus pi Or in other words, that I can restrict my choice of q from minus pi to 2 pi without losing anything. Because all what's outside this range is solutions that I can find also between minus pi and pi. So I just don't need to go outside my range. Okay, I think we'll stop here, and on Wednesday we'll continue with this discussion that will eventually lead us to understand Bloch's theorem. We're not going to prove Bloch's theorem. We're just going to understand it based on this example, this particular example of a one-dimensional chain. Any question? No. So the next test, I guess we're going to do it at the end of this week, on Friday. Okay? Good. Oh, question. Yes. We have been using this. So you're asking whether we can use the approximations that wave functions don't overlap. That's exactly what we've used to write this. Psi times psi is in principle the product of ai, aj times phi I, phi j. And we have assumed that because there is of this condition, phi I, phi j is delta ij. So we've been able to rewrite this as the sum of ai squared, using precisely this condition. So we've already used that condition, but we're still in trouble, because we're still summing over an infinite set of numbers. And if we claim that this is the correct solution, these numbers are 1. So we are in trouble. We need to find a way to normalize it properly. We'll come back to this problem. The solution is that we're going to normalize wave functions according to the unit cell. We're going to normalize them only by taking the integrals within the unit cells. Now, the counter argument could be, well, but the wave functions in a given unit cells don't need to be necessarily the same in the other unit cells. So how can we normalize in a given cell? What about all the other cells? Do we need to normalize them separately in all cells? And if you do that, I mean, do we have different coefficients for normalization? So it's something that will become much more clearer when we discuss Bloch's theorem. So I prefer to postpone the discussion to when we discuss Bloch's theorem. Yes? Why don't, sorry? The wave functions, so you want to say that the wave functions are the same in different unit cells. Why should they be the same? I mean, this solution, they are not the same. Because in one unit cell, I mean, if you jump from unit cell to unit cell, this coefficient will change, for example. So how are we going to handle this? The wave function is not the same. You might remember that Bloch's theorem tells you that wave functions, one of the, we'll come back to that, but you might remember, you've probably seen Bloch's theorem already in some form, right? So you probably remember that Bloch's theorem doesn't state that wave functions are periodic. It states something else. Wave functions don't need to be periodic. They are not periodic. Wave functions don't have the periodicity on the underlying lattice. This is an example, right? This wave function is not periodic. If you take an arbitrary q, this is not going to be periodic. No periodicity. Only if you choose q equals to 0 or 2 pi, then it becomes periodic. But otherwise, this is not periodic. So it is not true that wave functions need to be periodic. Something else is true, however, and we'll discuss it next time. Any more questions? Okay, see you on Wednesday.